Okay, so we're going to work through 21 through 40 on this. So 21, sulfuric acid found in some type of batteries. We don't care. What volume? So we know that we are looking for a volume of a 3.5 molar. Okay, so we are given a concentration. I think I know where this is going already. Is required to prepare 250 mils. Okay, that's another volume of a 1.25 molar solution, okay, of its concentration of H2SO4. So what we have here is, first of all, we're not changing substances. And so we know it's the same thing. And we know we're going from concentrated to less concentrated. So this is just simply a V1C1 equals V2C2. So this is a dilution problem. So V1C1 equals V2C2. I wish I had more space, but here we go. So volume 1 is what we're looking for because that's the more concentrated solution. And you could have set solution 1 as either, solution 2 is either. The concentration happened to be 3.50 molar. Volume we want to make is 250 mils and a concentration of 1.25 molar. There we go. So we're just going to solve for volume 1, which is essentially 250 times 1.25 divided by 350. We do the math, and you end up with, looks like 89.3. 89.3, not really sure why I switched color there. So we end up with C. So C is the answer here. It's just a simple dilution problem. C for 21. Okay. Sodium chloride is added to, looking at 22, sodium chloride is added to 25 mils of 0.1 molar silver nitrate. So we've got some information here. So 25 mils, that's volume. I'll use a different color. There we go. That's a volume of a 0.1 molar silver nitrate. Okay, so this is a concentration. What mass of sodium chloride? Okay, so what mass of sodium chloride? We're actually looking for a mass of NaCl. That's what we're looking for in order to completely react. So we know that we're switching from sodium chloride to silver nitrate because of this information, that orange information is silver nitrate, and we're looking for essentially we're looking for sodium chloride. So I know because I'm going from one chemical to another, this is a stoichiometry problem. So in order to do stoichiometry, we need a balanced chemical equation. And so that's where we start. Before we do that, I want to talk about stoichiometry, just so we're all clear and kind of how, if we remember how this works. So if we have a balanced chemical equation, let's say we have A plus 2B yields C. So if I start with some amount of A, and let's say that we have a solid for A, and I want to solve for, I don't know, a solid of B, as in I start with A and I want to know how much B I need in order for this reaction to completely go and completely do its thing. So if that's true, we always start with the mass of substance A, and we're looking for the mass of substance B. We cannot go directly to B, massive B, because we don't, they're way different amounts. So I can't say for every 1 gram of A, I need 2 grams of B according to this balanced chemical equation because of the stoichiometry. We can't do that because the masses are different. So we cannot go directly. We always, always, always have to convert to moles of A. N is moles. So we always have to convert to moles first. And we simply do that by using the molar mass. We always use molar mass of A. Going from grams to moles or moles to grams, you have to look at the periodic table. So we're going to use the molar mass of A. Once we get to moles of whatever substance we have, we always have to, we can then convert to moles of the substance we're looking for, but we have to do that using molar ratio. The molar ratio is just simply the number of moles of A versus B, or whatever substance you have versus what you're looking for. So in this case, for every 1 mole of A, I have 2 moles of B. That allows me to switch from one chemical to the other. And again, from a balanced chemical equation. So we always have to write out a balanced chemical equation. And then finally, in order to solve for the mass of B, we need to use molar mass of B. And that's it. Problem solved. We figure out the mass and we're done. This is not including limiting reagent. Well, I'm sure one of those will pop up and we'll talk about it then. But that's how we solve it. So that's if we're doing a solid. We are always going to have to do this step whenever we're doing stoichiometry, but we don't always start in the same place. The other possibility is that we're given instead of an aqueous substance or a solid substance, we're given an aqueous substance. So in that case, if I have aqueous A and I have aqueous B, in order to get to C, we are going to start with a volume instead. So let's say liters of A, and I want to convert to moles as I always do. And so in this case, if we're starting with something that's aqueous, we're always going to use molarity as the conversion because the units for molarity are in grams per mole, grams per, I'm sorry, grams per liter. I'm getting ahead of myself. Moles per liter. There we go. That's the unit. Moles per liter. And that's a conversion, right? So if it's 3.5 molar as an example, 3.5 moles per liter. So we can kind of use this in line. So we have liters or milliliters, which we convert to liters in order to figure it out. So when you're looking for moles from molarity, moles is equal to concentration, which is molarity times volume as long as it's in liters. But we're going to use this in line like we would any other conversion. So we're going to use molarity to go from liters of A, if it's aqueous, to moles of A. And then once we get to moles of B, again, through molar ratio, we can always solve for liters of B using the same exact thing, molarity, through the same exact process, just reversed. And of course, that would be if this happened to be aqueous as well, like I switched it to above. And then the last option is maybe everything is not aqueous, but we start with a gas and we end with a gas, or we start with a gas and we want to end with a gas. In this case, we're actually going to start with liters of A. Again, volume is going to be it. Oh, and we are going to convert to moles of A. Now, here's the thing. At standard temperature pressure, I'm just going to kind of put this caveat out there. At standard temperature pressure, we know that 22.4 liters equals 1 mole, and people love to use this as the answer because it's easy and it's straightforward, and you can use that as a conversion. My preference is to actually say, if I have liters of a gas to start and I want to figure out moles, we are actually going to use PV equals nRT to convert between moles and volume. This allows me to convert back and forth between moles and volume because they're both in the same equation, moles and volume and moles. Okay, so instead of using that 22.4 liters, just simply use PV equals nRT. You kind of have to take it aside and do it, but PV equals nRT to solve for moles of A. Then you convert to molar ratio to moles of B. And then we go from moles of B back to liters of B using PV equals nRT. And this is, again, if we're solving for a gas as the final thing. So in this case, in the case above, we are starting with an aqueous solution and we're ending with a solid. It's asking, we're starting with silver nitrate and we're ending with a solid, which means I have to convert to moles of A, then moles of B, and then to the solid. So we are going to take this path, right? If it's solid to solid, if it's aqueous to liters, you get the point. Essentially, we start one of these spots and we always go through moles to get there. Okay, so this is kind of the stoichiometry setup that we need. So with all of that said, let's take a look at this problem. I might need to take this aside. Let's see if I can do this. So I'm going to take this problem aside, copy, so I can kind of show you on here. Oh, that's not going to work. So, well, let's just do it here. If we need more space, we'll go grab it elsewhere. So sodium chloride is added to, so we need to create a, hopefully you aren't given one of these, but so I think this is just a 1-to-1 ratio, but AgNO3 plus NaCl yields AgCl plus NaNO3, and it's balanced. So this is a 1-to-1 ratio. So we're in good shape here. So in this case, we start with a volume. And so now we're going to essentially do, I'm just going to use this information and yeah, here we go. So my volume is 25 mils, but we're going to convert that to liters. And I'll show you why in a second. So 0.25 liters times fraction. And I guess I should say, yeah, I really want to take this down below. So I'm going to, so we're going to take this. Copy, and I'm going to do this information below. So here we go, paste. So this is the reaction. We have 0.025 liters of AgNO3. So we are going from AgNO3, which is aqueous, and we want to figure out NaCl, which is solid. So this is the conversion that we're doing. So times fraction, I want liters to go away. And because we are going from an aqueous solution to moles of AgNO3, we have to use the molarity. And it is in moles per liter. So I want moles in the top, liters in the bottom. Let's go look up the concentration. The concentration of silver nitrate is 0.1 moles per liter. So I'm going to plug in 0.10 moles per 1 liter. And that's why we have to convert the first thing to liters. Let me add the chemical. It's always important to add the chemical because we are going to be switching. Moles of AgNO3. Liters of AgNO3 cancels. Right now, if I stopped, I would be essentially here, moles of whatever substance I started with. Now I have to convert to moles of B. This is actually going to be pretty straightforward because it's a 1-to-1 ratio. So I want moles of AgNO3 to go away. And I want moles of NaCl to remain. And according to the balanced chemical equation, 1 mole of AgNO3 requires 1 mole of sodium chloride. So it's 1-to-1. Life is easy. Moles of AgNO3 cancel. And then the final step, now that I have my moles of AgNO3, or moles of NaCl, I'm trying to solve for solid. And so we're going to use molar mass. We use molar mass to go. So in order to do that, again, we're going to set up times fraction. I want moles of NaCl to go away. And I want grams of NaCl to remain. 1 mole of NaCl, I think it's 58.44. Let me just double check. Yep, 58.44. It's just kind of one of those numbers that you remember because you use it often as a teacher. So 58.44 grams per mole. Moles cancel, and I am left with grams of NaCl. Grams of NaCl. I always do my units first because I never mess it up if I have my units done. So in this case, I'm going to take 0.025 times 0.1, enter, times 1, times 58.44, enter. I end up with a mass of 1.1461 grams. 0.1461 grams. Let's check our answer. 0.146. There it is. So it looks like the answer for this is going to be C. 0.146 grams. And that's it. That's how we solve those. So what is the maximum number of grams of lead iodide precipitated upon mixing? Okay, upon mixing. This is a little bit different. This is a limiting reagent problem. So we have 2 starting points. So what we are looking for this one is I am looking for maximum grams of lead iodide. So this is, we are going to in this case, we are going to solid lead iodide. Okay. Yeah, I mean, there's no question mark there. We're going to a solid lead iodide, and that means that we're converting to grams of PbI2. upon mixing, but we have two different solutions here. We have 25 mils of 0.15 Ki, and we also have 15 mils of the lead nitrate. So this is a limiting reagent problem. I guess I'll work through and solve this because it's definitely worth doing. So in this case, I have a solution, and I'm going to do this below as well. So we need potassium iodide and lead nitrate. So let's create a new setup here. So lead nitrate, which is aqueous, plus potassium iodide, which is also aqueous, yields, we know that lead iodide, because we're good at double replacement reactions, which is a solid, plus the stuff that's left over, which is potassium nitrate and aqueous. We're not really going to care about the potassium nitrate, but let's balance this. And this is how I balance: one lead on both sides. Okay, we're good. I've got two nitrates here, and I only have one nitrate here, so I'm going to toss the two in front. And let's count again. One lead, good. Two nitrates, good. One potassium, two potassiums. I'm going to toss the two in front of here. And let's start again. Leads are good. Nitrates are good. Potassiums are good. Two iodides. Okay, so now that this thing is balanced, and I know that I am going to be going from lead to lead iodide. So I'm going from aqueous to a solid. And then again, I'll do the same thing, going from aqueous to a solid. In this case, this is a limiting reagent problem because the maximum number is actually the one that's going to give us the least amount, because that's the one that's going to stop the reaction. So when we do this, we know that so I'm going to start with the lead iodide or lead nitrate one, PbNO3 and which question is this? I should probably do that's 22 and 23. So this one was question 22. This one is question 23. And so it goes. So let's start. So let's start with lead nitrate as our starting material and see how much it ends up with. So my lead nitrate is 15 mils of a 0.5 molar or 0.175. So 15 mils, 0.175 molars. So 15 mils of 0.175 molar PbNO3. That's what I have in solution. I'm sorry, these are going to be pretty long just because these are complicated problems. So I always want to start with liters, because we are going to be multiplying by a unit of moles per liter. In this case, this is of lead nitrate. I always want to keep track of the chemical. I know it's extra writing PB, but it will make sure that we don't make any mistakes. 0.175 moles per 1 liter. At this point, liters of lead nitrate cancels. We want to figure out how much solid of PbI2 we make. So I want moles of lead nitrate to go away. And I want moles of lead iodide to remain. And we know that this is a 1-to-1 ratio because of the units out front. Moles of lead nitrate cancel. And if we stop right now, we'd be left with moles of lead iodide, but we want to take it one extra step. Moles of PbI2, 2 grams of PbI2. So let me just get the molar mass of lead iodide. You would obviously do this, but power of Google, PB, just faster this way, I2, 461.01. 461.01. All right, 461. That's giant, but okay, here we go. So 461.01 grams per 1 mole. Moles of lead iodide cancel. And now we just simply do the math. And so in order to do the math, let's see. So 0.015 times 0.175, enter, times the 461.01, enter. I would end up with 1.21 grams of PbI2. And that's it. So now let's try the other one. Let's start with my Ki and see how much I can get. So we have to check the concentration of Ki. My Ki is 25 mils of 0.15 molar, 25 mils of 0.15 molar, 25 mils of 0.15 molar. And off we go. And luckily we've got everything we need this time. So 0.025 liters, because I want liters to cancel, of my 0.15 moles of Ki per 1 liter of Ki times fraction. I want moles of Ki to go away. I want moles of PbI2 to remain. And let's just keep going. I want moles of PbI2 to go away. And I want grams of PbI2 to remain. So according to the balanced chemical equation, 2 moles of Ki produce 1 mole of lead iodide. So 2 moles of Ki produce 1 mole of lead iodide. And we know that this from above 461.01 grams of lead iodide is 1 mole of lead iodide. So liters cancel, moles of potassium iodide, moles of lead iodide cancel, and we are left with grams of PbI2, as we should be. And so now we just do the math. So 0.025 times 0.15, enter, divided by 2, enter, times 461.01, enter. I end up with 0.864 grams. So out of these two, the 0.864 grams of lead iodide, that's the limiting reagent. So that's the maximum allowed, because there's no way I can produce 1 gram of lead iodide if I only have enough to produce 0.864. So 0.864 is what we're looking at. 0.864, there we go. So this one is B. Okay. Oh, all right. If we run into more, probably just leave you guys up to it. All right. What is the net ionic equation for the reaction of magnesium sulfate and barium chloride? So this is a double replacement reaction. And we're looking for the net ionic equation. So this is the first one. So the net ionic equation. So if we're to write this out, we start with these two solutions, right? So we start with magnesium sulfate, aqueous, plus barium chloride, aqueous. Great. There we go. And then this is a double replacement reaction. I think we're going to need more room for this one as well. So let me just take this. This is the starting, yeah. So this is the starting. I'll just write that below. All right. So let's take, this is question 24. So question 24, let me add another page. Great. All right, so question 24, magnesium sulfate. So this first equation is going to be my complete molecular. So how I always do this, I'm complete molecular, and I'm going to turn this next one into complete ionic. And then after that, we have the net ionic, as well as spectators. This is always how I set it up. And what I want to do is I want to take my magnesium sulfate, anything aqueous. Actually, what this means is it's actually in its 2 ions. So magnesium 2 plus and SO4 2 minus. And if I'm not in the second complete ionic, I'm just not going to write aqueous because it's just tedious to do. And barium chloride is barium 2 plus and Cl minus. So those are this would be 2 chlorides, but I'm not going to worry about that. I just want to write the ions because I don't want there any confusion. Okay, so if we combine those two things together, So magnesium and sulfate were together before we mixed them, and they don't interact. I mean, they interact together because they're a solid, but once they're in solution, they go their separate ways. Once they're combined together, once all of this is in the same solution together, I have all four of these ions. So magnesium was with sulfate, but now it has another option. Magnesium can now join up with chlorine. And so we're going to say, I want to combine magnesium and chlorine to make a new compound out of that. And the other combination is barium as well as sulfate. So those are the combinations that we can have. And so what do we have? Well, magnesium MgCl2, because you do the little, I need 2 chlorides for every 1 magnesium. This is aqueous, plus 1 barium and 1 sulfate make barium sulfate, which turns out to be a solid. This is the solubility table stuff. So this is almost my complete molecular. I'm going to quickly balance it. 1 magnesium, good. 1 sulfate, good. 1 barium, good. 2 chlorides. So I actually don't have to do anything here. This is already balanced. So because this is balanced, now I'm just going to say anything that's aqueous gets rewritten as its ions for the complete ionic. So magnesium plus chloride. I don't need to write 2 chlorides, you certainly could. And anything that is not aqueous just gets rewritten as itself. So barium sulfate, I will indicate that this is a solid. So this is my complete molecular. If it asked for a complete molecular, this would be your answer. But what we need to do is we need to simply look at my complete ionic and eliminate anything that doesn't change. So in this case, magnesium is an aqueous on the left and it's aqueous on the right. I'm going to eliminate it because it doesn't do anything interesting. I'm going to add it to the list of spectator ions. This is just spectating. It's just watching the reaction. It's not doing anything else. And the other one is chloride. Chloride is the other spectator, just kind of watching the reaction because it's not really doing anything interesting. And if we look at the rest of it, sulfate becomes a solid, barium becomes a solid. So we have something interesting left. I'm going to rewrite everything that's left. Barium 2 plus aqueous. I'm going to add the phase tags now. Sulfate aqueous yields barium sulfate solid. This is the proper way to write it. You always write the positive one first. I think your test doesn't do that, but it should have. And here we go. So what I know is I have 2 spectators. I have the net ionic, and this is how you do it. You essentially separate it into these 3 reactions. We don't really care about the center one. That helps us get to the final net ionic, but that's the net ionic. Barium plus sulfate equals barium sulfate. So let's take a look. Barium, yeah, see, this one is backwards. Barium should be first, but we're going to say C for that one, okay? All right. Next up, a 25 ml sample of sulfuric acid is neutralized with sodium hydroxide, okay? What is the concentration of, so this is a 25 ml sample going to a, so there's a couple of ways you can solve this, but this is a neutralization reaction. So you write out your neutralization reaction, but this is also kind of stoichiometry as well. So this is a stoichiometry problem to some degree. So let's think about this. The other, it is a stoichiometry problem, but we can solve it in a bunch of different ways. So H2SO4 and NaOH. So first thing I always want to do, because I'm switching chemicals, because I have one and I'm interested in another, I always want to balance chemical equation. H2SO4 plus NaOH. And we're just going to switch partners. So I know it's neutralization, so I'm making water, and which is liquid, and I'm making sodium sulfate, Na2SO4. And again, we could do this the same way we did the previous one. Na plus, OH minus. So I'm going to combine together the other combinations. OH minus to make water, and sodium and sulfate to make sodium sulfate. But we don't really necessarily need to do that. So let's balance it. 2 hydrogens. By the way, the other way that I usually represent, water represents H plus and OH minus together. So that's kind of how we can look at it when we're balancing as well. So I have two hydrogens here, and I actually only have one because we have to look at it like this. So I'm going to say, I'm going to put a 2 in front here, and you'll see that it's going to work out. So 2 hydrogens, 1 hydrogen, but putting a 2 in front like I did here, 2 hydrogens, 1 sulfate, 1 sulfate. Now I have 2 sodiums, 2 sodiums, 2 hydroxide, 2 hydroxide, because I'm representing it as HOH. Okay, and so there it is, it's balanced now. So what I know is 1 mole of H2SO4 requires 2 moles of NaOH. So really this question is asking how many moles of what do we have here? What is the concentration of sulfuric acid if 35 mils? Okay, so 35 mils of a 0.15 molar solution, and we have a 25 mil sample of H2SO4. So we have 25 mils of H2SO4. Okay, so how many moles of sulfuric or sodium hydroxide do I have? Again, 0.35 liters times fraction. I want liters on the bottom, moles on the top. 0.150 moles is 1 liter. Liters cancel, and I'm going to be left with, what is that? 0.035 times 0.15 gives me 0.00525 moles of NaOH. Well, what I do know is if I start with that, and probably need a little more room here, so I'm gonna erase all of, well, I'll just move it. So if I know that that's true, 0.0052, and this could be set up as stoichiometry, moles of NaOH times fraction moles of NaOH on the bottom and moles of H2SO4 on the top. So in order for this reaction to proceed, 1 mole of H2SO4 is equivalent to 2 moles of NaOH according to the balanced chemical equation, right? So what we do is we solve this and we end up with, so I divide my answer by 2, right? And I end up with 0.002625 moles. Too many sig figs, it doesn't matter. So that's how many moles of sulfuric acid I need divided by the current volume of 0.25 liters. That's 25 mils, right? The 25 mils I have. So all I need to do is essentially figure out what the volume is by dividing by 5. So the concentration is 1.05 molar. There we go. So again, the idea being is I need to know how much H2SO4 we completely reacted, and I solved that with stoichiometry. And so my concentration should be 0.15 molar. Turns out B is the answer, 0.105 molar. That's it. A little more complicated, but same kind of idea. You're still using the same concept, right? You can use this actually because we start with a solution, we end with a solution, but instead of going to liters, we figure out how many moles we have because we already have the volume. So here to here to here, and then use the liters that we already have to figure out what the concentration actually was. It's a little bit different, but kind of the same in terms of what we're looking at. All right, so hopefully they get shorter from here because this has been a long video already. All right, determine the oxidation number of the bolded of each. Okay, we can do that. When we're doing these, the simple way to do it is the way that I tell my students to do it. So H2. So let's take a look at H2PO4 minus first. What do I know? Well, up top, I'm going to do the individual charge or oxidation state. Underneath, I'm going to do the total atom charge. So as an example, like all of the hydrogen, right? And then over here, this whole thing is actually, this is the compound charge or ion compound charge. In this case, the whole thing, whatever all of the atoms are, has got to equal what the total ion charge is. So which ones of these, we'll know all but one. I know that oxygen is going to be -2. So I have 4 oxygens. So there's my oxygen plus my phosphorus plus my hydrogen. So I know that I have 4 oxygens at a -2 charge. So the total charge for all of the oxygen is -8. Out of the hydrogen and the phosphorus, I trust hydrogen more because it's on the edges of the periodic table. Hydrogen is going to be +1. I have 2 hydrogens, so the total charge for hydrogen is +2. So now it's a matter of what has to go here in order to make the rest of this math equation 2. Well, I want the entire thing to be -1. Okay, so I need a +5 here in order to make this math true, right? So 7 minus 8 gives me -1. So I need my phosphorus to be +5. And there we go. Phosphorus is +5. So that eliminates A right off the bat. And so we do the same thing for each of these. If oxygen is -2, this whole thing is -6. Everything is -2 altogether. So what has to go in the sulfur? Sulfur has to be +4. So +4 for sulfur in order to make all of that true. So that eliminates B. N2O, I know that oxygen is -2. So the total of -8, the whole thing is neutral. What has to go in the math? Well, I need +8 here. So one of these nitrogens has to be +4. And so that eliminates D. So the correct answer for this one is going to be C. Again, which ones do we know versus, and we kind of always work in the same direction. We go from what we know to what we don't. What we know to what we don't. All right. Moving on. What is the reducing agent for the following reaction? Okay, so we need to assign some charges. The thing you should do when solving these is always look at metals first, because you're always going to have oxidation is loss, reduction is gain. You might do Leo-Gur or something like that. So we're always going to have both of them. Oxidation is loss, reduction is gain. By the way, the same element can be both oxidized and reduced, so always check. Oxidation is loss, reduction is gain. It usually happens to metals, so we're going to focus on the metals first. So let's assign oxidation states to just metals to start. So anything all by itself is going to be neutral. So zinc is neutral here. Manganese, well, I know oxygen is -2, so -4 total, plus the whole thing is neutral. Manganese has to be +4, so +4. So hopefully you get the sense now. So zinc, manganese, and now let's check zinc and manganese on the other side. We can kind of skip ahead. I know that OH is a -1 charge. That makes zinc a +2 charge. Zinc is a +2 charge. I know that hydroxide is -1. I know that oxygen is -2. This makes the manganese in this case +3. Okay, so in this case, oxidation is loss, reduction is gain. So here's my zinc, here's my manganese. My zinc goes from 0 to +2, my manganese goes from +4 to +3. Okay, so we found 2 that change. It's mostly often the metals. So oxidation is loss, reduction is gain. So going from 0 to +2, I'm positive I lost an electron. Becoming more positive means you're losing electrons. So what that means is zinc going to zinc 2+ is oxidation. Manganese going from +4 to manganese +3, where it's gained electrons because it's dropped in a charge, is going to be reduced. So what is the reducing agent? So we know what's oxidized and we know what's reduced. So the way that we always look at this, because reducing agents and oxidizing agents, it sounds weird. So now that we know that it's this and this, manganese and zinc, oxidized, reduced. whatever's oxidized and reduced, we're always going to look at just the element. So zinc is oxidized, manganese is reduced. And now I want to look at the oxidizing agent and the reducing agent. And here's the trick for oxidizing and reducing agent. The reducing agent contains the thing that was oxidized. The oxidizing agent contains the things that was reduced. But the important thing is it has to be the entire chemical, only reactants. So we actually don't even care about anything over here in the end. We want only reactants. So the oxidizing agent contains the manganese. So MnO2. And which I don't even think they have phases. They should have phases, but they don't. And the thing containing the zinc as a reactant is just zinc solid. So what is the reducing agent? Well, since zinc is oxidized, it is going to be A in this case. So zinc is oxidized, the reducing agent turns out to be zinc. Zinc 27 should be A. Yeah, all right. My God, this is a lot. All right. What volume of oxygen gas in a balloon at 1 atmosphere, 305 K and 0.65 liters? Calculate the volume after. Okay, so when we're doing gas problems, I'm going to highlight information I have. Atmospheres. That's a volume. Nope, that's a pressure. Just kidding. Pressure. We're not going to add anything else. That's a pressure. Next up, 305 K. We know that's a temperature. Next up, 0.65 liters. We know that that's a volume. Calculate the volume after the temperature is lowered. Temperature is lowered. So this is a changing event. I started with one state of gas and now I'm switching. So now I have a new temperature while keeping the pressure and the amount of O2 constant. So actually, we have changed the temperature. So we're going to call this temperature 1, volume 1, pressure 1, temperature 2. What is the volume? Calculate the volume. So we're looking for volume 2 because we know the temperature. Pressure is constant, so I don't really care about this pressure because it's not included because it's constant, so we can ignore it. And the amount, so the moles do not change. So we know P1 V1 over N1 T1. I did this in the very initial question on the first video. P2 V2 over N2 T2, and I can eliminate pressure and moles. So eliminate pressure, eliminate moles, and now it just becomes a plug and chug equation. Volume, temperature, your temperature has to be in Kelvin. Luckily, our temperature is in Kelvin. And we are looking for a volume. They're all in liters. So 28, let me just look this up. 28 is A. You don't need to see me do the math. 28 is A. So that's what you should get for a volume. Again, gas law stuff. All right. At a constant temperature, a sample of gas. So again, same thing. A sample of gas is initially at 0.0 atmospheres. Okay, so we've got a pressure. Is compressed from initial volume. Okay, so now I have a new volume, 2 volumes here. So we're going to call this volume 1, volume 2, maybe. This is also the same type of question, okay? Because is compressed, there is the activating thing. I had one state of gas and now I've got a different state of gas. So we are going to solve 29 with the exact same equation with pressure. And so I'm not going to eliminate pressure. So the equation that we're going to use in this case is P1 V1 equals P2 V2. We care about the final because nothing changed. Constant temperature, we can eliminate temperature, and we can eliminate moles because there's no mention of them. So 29 is D. So you're going to end up with D for this one. So again, just a plug and chug. I'm not going to walk through that because this video is already super long. How many moles of helium are found in a balloon that contains, okay, again, another gas law problem, 0.5, that's a volume. Helium at a pressure, so we've got a pressure. Okay, so that's pressure. and a temperature. Okay, I've got temperature of, first thing I want to think about is temperature is 22 degrees Celsius plus 273, right? So we always want to change it. So 295 K. We always want it in Kelvin because you can't have a negative temperature. Notice that there is no change, right? These are all the same. So because it's one state, states don't change. There's no second pressure and volume, temperature, moles. We're just simply going to use PV equals nRT. That's the equation that we use. R is given on your crib sheet. And it's just a plug and chug as well. B should be your answer for the number of moles. By the way, you would also use PV equals nRT in a stoichiometry sense as well. All right, 31. A gas phase mixture of H2 and N2 has a total pressure of 784 torr and a partial pressure of 100. What mass? Okay, so this is a lot going on. This is partial pressures as well as PV equals nRT. So actually this is going to be not too bad. So a gas phase mixture of H2 and N2. So what this means, having those two things present together, means that the total pressure is equal to the pressure of H2 and N2, or N2 and H2, as I wrote it, right? So the total pressure of 784 torr with a partial pressure of H2 of 124. What is the mass of N2? So we're looking for the volume of N2 gas. And so we've got a liters, we've got a temperature. Oh, it's insane. But so volume and temperature, but it's already in mils. That's good. So my pressure of N2 is going to be, what's that? So 660, I think that's right, 660 torr. We're gonna have to change this. We're gonna have to convert, but 660. Okay, so now I've got pressure, but it's asking for mass of N2. Okay, so this seems complicated, but it's not. This is a gas problem. Has anything changed? No, we're dealing with one state, which means that we are going to be using PV equals nRT. So if we look at PV equals nRT, I have the pressure of N2, but we're going to have to convert this to atmospheres. I have the volume, I believe. Yep, we have volume. Yep, check. We're looking for moles. I'll talk about why. We have R because it's a constant, and we have temperature. So you solve for moles. And once you have moles, because I know it's N2, I'm going to convert to, with using molar mass of N2, I'm going to convert to grams of N2. That's how you solve this one. I don't want to walk through this one either because it's more annoying than anything. And I've got to make this a little bit quicker. 31, you should end up with D. So D should be your answer. It's actually quite a bit of nitrogen. But anyway, so that's how you solve it. So use the pressure, plug it into PV equals nRT, solve for moles. Once you have moles, use molar mass to convert to grams. That's it. Again, if you don't have a shift in state, no different pressure, no different volume, no different temperature, then it's just PV equals nRT. Okay, next one, 32. Acetylene may be produced from the reaction between calcium carbonate and water. How many moles of acetylene are present in a 500 ml sample? Okay, so volume. All right, so volume collected over water at 20 degrees Celsius. Okay, temperature, the total pressure of 785, and the vapor pressure of water is, okay, so this is asking, this is the same exact question. This is the same exact question. So the P total, and we did this in lab, P total is equal to all of the pressures present. Anytime you collect something over water, we always have to keep in mind that whatever the pressure of water is, the vapor pressure of water is going to be included, as well as, what did we collect? Acetylene, pressure of acetylene, which is HCN. No, that's not it. CH3, doesn't matter. I'll just say acetylene because you're not going to know what I'm talking about. All right, so we know the pressure total, 758. We know the vapor pressure of water is 17.54. So The acetylene is that right there, 758 minus 17.54. And once you have the pressure of acetylene, we follow through with the same thing. How many moles, but you're just going to stop at moles. You don't have to convert it to mass because I don't think they give you, they don't tell you what acetylene is anyway. So 32 was B. So you should end up with B here. I'm happy to walk through these at some point. If you really need to see them, let me know, but we're going to convert that to moles. But it's the same kind of thing as 31. Just recognize that vapor pressure includes all of the stuff present, including water. Okay, what mass of water vapor is produced from the gas phase reaction of O2 with H2? Okay, and a lot going on here. So here's my reaction. What mass of water vapor is produced? Okay, so again, what mass of water vapor? So I am looking for a mass of H2O is produced from the gas phase reaction. Okay, so this reaction right here. In a 2.5 liter at 28 degrees Celsius, pressures of O2 and H2 are 0.98 and 0.1 to 0.24. So these pressures allow us to get, by the way, pressure is just concentration when we're looking at it too. H2O2, pressures, okay. So this is pretty annoying. This is a limiting reagent problem as well as stoichiometry. So we go back to, if we go to our stoichiometry situation, I'm going to solve for, all right, so what I'm going to do is I'm going to say, I'm going to take the liters of O2, which we have, okay? Yep. I am going to convert to moles of O2 and then convert that to moles of H2O and then convert that to grams of H2O. So this is a stoichiometry problem. Liters, we're going to use PV equals nRT, but the pressure is going to be the pressure that's designated, okay? Because that will give us moles ultimately. And then you plug in, you do molar ratio. And then finally you do molar mass of H2O. And then you do the same thing, but this time you do it for hydrogen and a concentration of this, and make sure you're using your stoichiometry. And 33 turns out to be B. So this is a stoichiometry problem. Figure out how many moles of oxygen you have, convert to moles of water, convert to grams of water. Then do the same thing for hydrogen. How many moles of hydrogen, convert that to water, convert that to grams. Okay. Next one, how many moles of nitrogen are needed to react with, this is another stoichiometry problem. So again, another stoichiometry problem, the same exact way. Maybe I will do this one. Because I have space, I'm going to do this one just because it's going to be, just so you can see how I did the one above. So how many moles of nitrogen are needed to react? So how many moles of nitrogen? So I'm looking for just simply moles of nitrogen needed to react with 1.5 liters. So there's a volume of H2. Gas measured at 20 degrees Celsius, 273. So this is, so plus 273. We always need Kelvin. So 293 K and 0.95 atmospheres. So PV equals nRT. My pressure is 0.95 atmospheres. My volume has to be in liters, but I think that's what, no, I do have one, 1.5 liters. I'm looking for moles of hydrogen. My R is 0.08206 liter atmospheres per mole, okay? And my temperature is 293 Kelvin, assuming I did my math right. And so here we go, 0.08206 times 293. Let's see this again. 206 times 293, enter. Divide by 1.5, enter, divide by 0.95, enter. So the moles in this case is 16.9 moles. My God, that seems really high. Let me just try this one more time. 0.08206 times 293, right? Yeah. Divided by 0.95, enter. Divided by 1.5 liters of nitrogen, 273.95. 206. All right, well, here we go. 16.9 moles. What's the answer for this one? All right, let me see. 34 is B. Yeah, I think this question is wrong, honestly, but here we go. All right, so that one is going to be B as well. All right, well, here we go. Let's take a look. So I have 16.9 moles of H2, maybe not, times fraction. I want moles of H2 to go away, and I want moles of N2 to remain. So 1 mole of N2 is equivalent to 3 moles of H2. So I'm going to divide my number by 3. 5.62 moles N2. Yeah, I don't know what happened here because this just doesn't seem right. Seems like a really small quantity too. Why did I get such a large number? P equals N. Oh, I'm sorry. I did this backwards. Look at me. I should have moved the stuff over the other side. Sorry, I'm just doing a lot here. That's why. Oh, I guess I can leave that. Let's get rid of this number. Oh, glad I caught it. See, the numbers don't make sense. And so I'm going to solve for moles. Let me properly solve for moles. So instead, I'm going to do 0.95. I did it the other way, times 1.5. 0.5. Oh, God. All right, let's try one more time. 0.95 times 1.5, entered, divided by 0.08206, entered, divided by 293. This is what happens when you do thousands of calculations all at once and really early. 0.059, 05926, so 593, 0.0593. Perfect. Divided by 3, enter, gives me 0.019. Better. Stoichiometry, this gives me 0.0197 or 198, 0.0198, 0.0198, or 0.2. Yeah, there we go. Whew, I'm glad we caught it. So this was moles of H2. And plug it in. Stoichiometry, if we need to convert to grams, we just use the molar mass of nitrogen in this case. But yeah, so in the end, we end up with moles of N2. All right, perfect. Moving on. A gas sample A has a molar mass 3 times that of B. Which one moves faster and by how much? So this is, you should have the equation for this. This isn't a fusion thing. And so what you end up with is molar mass of A divided by molar mass of B. Let me just make sure that, right. Right, yes, it is going to be based on the molar mass. I've got that upside down. So the rate of gas A as a function of the rate of gas B. Let me see. How much times molar has a molar mass 3 times that of B? Which one moves faster and by how much? We're going to flip this over, the molar mass of A over molar mass of B, and we're going to take the square root. And so we can just plug numbers in. Ultimately, it says A has a molar mass 3 times that of B. So ultimately what that means is 1/3. What is the square root of 1/3? I mean, we could look at it that way because we want to compare A to B. So 1/3, enter, and then I'm going to take the cube root. I don't know that I can do it, but I can raise it to 1/3 though. third, enter. So 0.69. And I can take the inverse of that actually. And so it's not 3 times faster. It's the smaller, and okay, so we'd actually, that's the diffusion equation, but it's not 3 times faster. It's based on the essentially the square root of the two gases. So we know that the smaller one is faster. So we know that B is faster, and it's not 3 times faster. It would be C, 1.7 times faster. Yeah, should be C anyway. Let me double check. Yep, it is. 35 is C. There we go. All right. 36. What is the internal energy for a system that has and loses heat? Okay, so in change in energy, Q plus W. So we have to think about the direction, the signs. This is really asking those two combined for a system that does 422 joules of work and loses 227 joules of energy. Yeah, so does work. That means it's doing work on the surroundings. That makes this a negative. And it loses energy. For a system that loses energy, it's losing it into the surroundings. So that's negative. It's going out. If it's going out of the system into the surroundings, it's losing that energy. It's releasing it ultimately. That's negative as well. Answer is B. So that becomes a question. That becomes a question of essentially the sign of those two things. Okay, next up, 37. Identical amounts of heat were applied to 100 grams of each of the substances below, all initially at 25 degrees Celsius. Which one will have the highest final temperature? Okay, equal amount of heat. The highest temperature is the one with the lowest heat capacity, right? If you think about the unit, joules per gram degree C, copper, let's see here. It looks like mercury. Mercury will increase the most. So for every 0.14 joules, 1 gram of it goes up 1 degree Celsius for mercury. Because it has the lowest, every joule does more, right? So 37 should be A. There we go. Yep. Mercury is going to go up the fastest because energy goes a long way in heating it up. All right, a 3.54 gram piece of aluminum is heated to 96.2 degrees Celsius and allowed to cool to room temperature. Okay, so my delta T in this case is equal to 96.2 degrees Celsius minus 22.5 degrees Celsius. I'm measuring this, so 96.2 minus 22.5, because it started high and it ended at room temperature. So it's a 73.7 degrees C swing. Allowed to cool to room temperature. What is the heat associated with the cooling process? So that's the temperature change. And what we know for aluminum is for every, we know that it's a 3 point. So just use the units. Okay, so what I want to do is I'm going to start with 0.903. If you don't know the equation, just use your units. Grams per degree K. Same thing as at 1 degree C, so we can just say degree C as well, times degree C. I want joules as my answer, right? Or kilojoules as my answer. So what I want to do is I want to cancel grams and degree C. So I need to multiply it by the grams, 3.54 grams, and I need to multiply it by the 73.7 degrees C. So when I multiply that out, 0.903 times 3.54, enter, times 3.7, I get a total of 235 or 236 joules of energy, because grams cancel, degrees C cancels, and I'm left with just energy. But we want it in kilojoules, so 0.236 kilojoules, 0.236 kilojoules. And so that eliminates these two. So it's either D or A. And so what is the heat associated with the cooling process of aluminum? So we have to ultimately ask ourselves, did it lose heat or did it gain heat? So it is the system being the aluminum, it's releasing heat into the surroundings. So the water is cool. So it's cooling. So it's releasing heat into the surroundings. That is going to be a negative. So we should have D for 38. 38D. There we go. All right, two more. 1.5 gram. This is the same type of question. Okay, so 1.5 grams of iron heated to 95, placed in water. This change of water, final equilibrium temperature, the specific heat capacity of those two things. What is the overall heat transfer of this? So initial temperature, final temperature. So your delta T, iron, and the specific heat capacity of the iron. So the iron goes from 95 to 57.8 degrees. This is the same thing you guys did in lab. 1.5 grams of iron, again, multiply by the delta T, and the same exact problem as the previous, said in a different way. You should end up with B, I guess, here. 39 was B. Yeah. All right. A volume of a gas expands against, or okay, so final one, thank God. External pressure, okay. Pressure, volume, volume. How much work is done? So we're looking for external, so we have pressure. Oh, I thought this was a gas problem. It is not. Pressure, volume, volume. And so now we are essentially, we have some amount of gas doing work on the surroundings. So work is equal to pressure times or essentially force, which is pressure times displacement. Okay. You want to make sure that your pressure is in pascals and your volume is in meters cubed, or you could do kilopascals but anyway, meters cubed. I don't know what equations you guys are actually getting for here, but typically you want to switch to pascals and meters cubed. It's annoying, but your delta V and your pressure, that's essentially what you're looking for. Yeah, yeah. So I'm not sure exactly. Yeah. So in any event, that's the math that you're going to do, and it's been long for me. So 40 is going to be D. So yeah, your pressure. I mean, there's a couple of ways to look at it as well, but it is your work is pressure times your delta V. So 0.943 atmospheres. Yeah, but you need to convert that to pascals ultimately to get the proper answer. Yeah. Okay, so that's 1 through 40, and two more videos coming.